On this worksheet, we're going to do a few different types of calculations that involve use of the standard reduction potential. In the first problem, we're calculating the voltage of a cell that is made from copper and copper 2+, and also lead and lead 2+. The equation that we use to calculate the voltage of a cell is E cell standard equals E cat minus E an, where that is the reduction potential at the cathode minus the reduction potential at the anode. We need to use a table of half reactions, which I have over here, to look up the reduction potential of the copper to copper 2+ and also the lead to lead 2+ half reactions. So I'm just going to kind of make a note over here. We have a copper and copper 2+ half reaction, and we also have a lead and lead 2+ reaction. And we're going to go over to this table of half reactions. We're going to find each one of these cells and write their voltage down. This particular table of half reactions is listed alphabetically. Some of them are listed by voltage. And I am going to begin by looking for the copper 2+. And we do want to be careful, especially with copper. There are three different types of copper reactions here. We want to find the one that involves the copper atom and the copper 2+ ion, which is this first one right here. So this specifically is the one that we're looking for. I'm just going to kind of move it up to the top. I'm going to make a little note here. And then to get the voltage of this, I'm just going to scroll over. So here's the voltage of that half reaction. It is 0.3419 volts. And now we're going to look for the lead and lead 2+, this one right here. Here is there's only one lead half reaction, lead 2+ and lead. The voltage for that is negative 0.1262 volts. So we're just going to take these two numbers and plug them into this equation. We need to plug in the voltage of the cathode first and the anode second. And fortunately, it's not telling us directly which is at the cathode and which is at the anode, but keep in mind that E cell is always a positive number. So we just simply need to plug these values into this equation in a way that will give us a positive result. One way will give us a positive result and another way will give us a negative result, and that's the case every single time. There's only going to be one way that you can put these numbers into this equation and end up with a positive result. And so that for us, that is going to be 0.3419 minus a negative 0.1262, which gives us 0.3419 minus negative 0.1262. A voltage of positive 0.4681 volts. The next problem that we're looking at is giving us the actual reaction for the galvanic cell. It wants us to identify and write an equation for the half reaction taking place at the cathode and also at the anode and calculate the voltage of the cell. So this one is a little bit trickier because we are going to have to pull the two half reactions out of this equation. However, we do have all of the half reactions written out in this table, which is actually going to help us kind of move through this problem pretty quickly. So what I'm going to do with this, I'm going to begin by getting ready to identify the two half reactions in this equation. So using a similar process that we would use if we were being asked to balance this. So by that, I mean, I'm identifying that I have this copper 2+ ion, and I want to look over on the right-hand side to see what that is corresponding to, what it's matching up with. I have a copper +1 ion over here. And so, it makes sense to me that I'm going to keep these two chemicals together because they're both copper. I'm going to keep them together in a half reaction. And then for my other substances, I have the H2 and OH- hydrogen and oxygen atoms going to H2O. So I've just kind of highlighted sort of the basics of the two half reactions. What I'm going to do now is go to this table of half reactions and I'm going to find a reaction that involves copper 2+ and copper plus. Going back to my coppers. So here that I have up at the top, here is the copper 2+ and copper +1 reaction. It's not exactly the same as what we have in the overall equation that's provided to us. The stoichiometric coefficient is different, but that's okay. We totally know how to handle that. So I'm going to use this as kind of like my skeleton because it has the electrons written into it, but I'm going to modify this half reaction so that it matches up with the stoichiometric coefficients that I have in this overall equation. And that just simply means I'm going to take this half reaction here and I'm going to multiply it by 2. So I've got 2 Cu2+ aqueous plus 2 electrons, making 2 Cu plus aqueous. And again, all that I'm doing is I'm taking this equation up here and I'm multiplying everything by 2. And then while I'm up here with this equation, while I have it handy, I'm going to write the voltage down. The voltage for this is 0.153. Now, in terms of voltage, even if we make a modification to the stoichiometry of a reaction, we don't ever do anything to the value of the voltage from the cell. So no matter what you might be doing to the half reaction in terms of coefficients or turning it around or whatever, this number always stays exactly the same, no matter what. So here's one of our half reactions. Now I'm going to go look for the other half reaction. I'm going to find something that involves hydrogens and oxygens. There are a few different half reactions involving hydrogens and oxygens, so I'm going to be a little bit careful. It looks like this one right here is the one that we're looking for, but you've got to look at it pretty closely. It has 2 H2O liquid, which we have on the right hand side, and then on in this one on the left hand side it has H2 gas and 2 OH minus aqueous. So it is the same. This is the half reaction that we're looking for. It just has been turned around. So I'm just going to reverse. I'm going to take this equation here, but I'm going to write it in reverse. H2 gas plus 2 OH minus aqueous makes 2 H2O liquid and 2 electrons. And then again, I'm going to copy the voltage. And again, no matter what we do to the equation, we don't make any changes to the voltage, the value of the voltage. I'll talk about that a little bit in just a second. Okay, so we have, we've written a balanced equation for both of the half reactions. We haven't identified which is which yet, and all we need to do is calculate the voltage of a cell. So we just need to identify, is this happening at the anode or is it happening at the cathode? Let's kind of keep in mind our tricks that we have. We have oil rig. That tells us that the oxidation is loss of electrons and the reduction is gain of electrons. Oxidation is loss. This is the substance. These are the substances that are losing electrons. So this is our oxidation. This is our reduction. Reduction is the adding or the gaining of electrons. We also have the trick red cat, which reminds us that the reduction is taking place at the cathode and the oxidation is taking place at the anode. And then last but not least, calculate the voltage of the cell using our equation E cell equals cathode minus anode. So we're just going to plug in the value at the cathode, which is 0.153, and we're also going to plug in the value at the anode. Now remember, we turned this equation around and I said don't change the sign on this, leave it a negative sign. Here's why. The equation is built in with a negative sign. That negative sign is built in to reverse the voltage of the half reaction. So if you turn the voltage around and then plug it into the E cell equation, it's just going to turn itself right back around again. 0.153 minus a negative 0.8277 is 0.9807 volts. Here's a similar problem. We have two half reactions. Voltages have been provided. We're supposed to write a balanced equation for the reduction and for the oxidation and for the overall. Oh, and also calculate the voltage of the cell. Both of these are written as reduction reactions. Reduction is the gain of electrons, so they're both showing electrons on the left-hand side. That's impossible. One of these reactions has to be an oxidation, which means one of these reactions is going to need to be turned around. We have to figure out which one needs to be turned around. So we're going to start by calculating the voltage of the reaction. E cell is cathode minus anode, and we're going to, as we do this, we're going to remember that the voltage has to be a positive number. So we want to plug these two numbers in to this equation in a way that's going to give us a positive answer. And again, there's only one way to plug them in and get a positive answer. Minus 0.771 minus a negative 0.13. We want to take the bigger number and subtract the smaller number. 0.771 minus a negative 0.13 is 0.91 901 volts. Now doing this, starting off with this, allows us to identify which is the cathode and which is the anode. When we plugged these in, we plugged in the 0.771 volts as the value of the cathode. So that tells us that this is the reaction that takes place at the cathode. This is the reaction that takes place at the anode. The reduction reaction is the one that takes place at the cathode because red cat. This is the one that takes place at the anode. And so now that we know that, we know which one we need to turn around. Reduction is gain of electrons or adding electrons. So this equation right here is correct in the way that it is written. It is being written as a reduction reaction, and that's what it needs to be written as. This reaction, however, is actually an oxidation reaction, and currently it's written as a reduction reaction. So this reaction right here needs to be turned around. So the reduction reaction, balance it. We're going to just copy it. It is going to be Fe3 plus electrons. I'm leaving the states off just to save time and space. Fe2 plus. The oxidation reaction, I'm going to turn it around. CrOH3 plus 5OH minus makes CrO4 2 minus plus 4H2O plus 3 electrons. And again, this is my reduction, and this is my oxidation. Last, it tells us to write a balanced equation for the overall reaction, so that means we need to combine these two equations together. In order to combine them, they need to have the same number of electrons, so that means I need to change the stoichiometric coefficients to 3 for the reduction reaction. And then when I combine them together, remember those electrons are going to get canceled out. I'm going to have 3 Fe3 plus CrOH3 plus 5OH minus makes 3 Fe2 plus CrO4 2 minus plus 4H2O. We have one more problem on this worksheet that we can do. That's similar to the last one, so I'm going to get rid of this table of half reactions. We don't need it anymore. We get to practice this one more time. We have two reactions, both written as reduction reactions. We're going to calculate the voltage of the cell, write out the half reaction for the reduction, also for the oxidation, and the overall equation. We're going to start by calculating E cell. E cell is the cathode minus the anode, and E cell is always a positive number. So we want to look at these two values. We want to take the larger number first, 1.359, subtract the smaller number. This way we're going to end up with a positive voltage. 1.359 minus 1.23 is 0.129 volts. When we set this equation up in a way that gives us a positive voltage, it also identifies for us which half reaction is taking place at the cathode and which is taking place at the anode. The reaction with the voltage of 1.539 is the reaction that's taking place at the cathode, and the other is the one taking place at the anode. From our trick red cat, we know that the reduction reaction is the one that is taking place at the cathode, and the oxidation is the one that's taking place at the anode. Also from our trick oil rig, we know that the reduction reaction is the one involving the gain of electrons. So this reaction right here is written correctly, exactly like it needs to be written. Cl2 plus 2 electrons makes 2 Cl minus. The oxidation reaction is the reaction that involves the loss of electrons. Currently it's being written as a reduction, so we just need to turn this equation around. We just need to reverse it. 2H2O plus, 2H2O makes O2 plus 4H plus 4 electrons. And again, this is our oxidation, and this is our reduction. The last thing that we're asked to do is combine them into an overall equation. In order to combine them, we need to have the same number of electrons in each one of the half reactions. So that means that we need to multiply the stoichiometric coefficient in the reduction reaction by 2 so that we have the same number of electrons in both, and then we can combine them together. 2Cl2 plus 2H2O. I'm just omitting the height of the electrons from this. This makes 4Cl minus plus O2 plus 4H plus.